Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're going to have a discussion on an enrichment of area. You know, every so often when I'm having my cup of tea in the morning, the Salada tea bags have these sayings on them. And when you have that many sayings, you're going to see some brilliant ones and some not so brilliant ones. For those of you who have survived the course this far and are finding it a little bit difficult, and maybe you feel you're struggling, I thought you might appreciate one of the sayings. And what it said was, he who wishes to occupy a place in the sun has to expect to get blistered. We all want the tans, but nobody wants the blisters. And just keep staying with us, because we're getting into the stuff that, even though this seems like we started at very elementary origins, it's quite advanced and complex. On the flip side, I saw another Salada tea bag, and all it said was, "Blessed be they who go around in circles, for they shall be known as wheels." And on that note, I would like to get into our discussion today. Basically, even though it's a continuation of area, it's a region that, next to straight line regions, is perhaps the most famous and well-known region there is, and that's the circular region. And I thought I'd like to teach you a little bit about perimeter and areas as applied to circles. And so, without any further ado, we'll just entitle today's lecture, "Circles, if you've seen one, you've seen them all." And I'll explain what that means very, very shortly. First of all, let me show you the traditional way in which a circle is generated. Let's suppose I'm hunting for something, and I have an instrument, and this instrument tells me that what I'm hunting for is within 3 miles of where I am. But it doesn't tell me in what direction. So what I know is, if I head off in this direction, within 3 miles of my starting point, the object will be there, provided it's on that line. In fact, to make this problem easier, let's assume that my measuring device has told me it's exactly 3 miles away. So if I were going in this direction, it would be over here. And if I were going in this direction, it would be over here. And if I were going in this direction, it would be over here, etc. The problem is, I don't know what direction I'm going in. But as you look at how these points arrange themselves, you begin to see what is meant by a circle. You see, as I've described this problem, all of these points are 3 points from my starting point. And basically, there is a very simple construction in geometry that allows you to locate all of these points. What you do is you take a piece of string drawn to scale to represent 3 miles. You put one end of the string at the starting point, which we'll call our center. See, S is for center. I'm a math specialist, not a spelling specialist. Then you take the piece of string, and holding this end fixed, you just swing the string around, and it will generate what's called a circle. And in fact, you've probably seen these things. They have devices called compasses, where basically there are 2 poles. There's a pin at one end and a pencil being held at the other end. You put the pin down at the center, adjust the distance to whatever length you want, and you then swing a circle, so to speak. And basically, this is the figure you get. And let's just learn a little bit of vocabulary. By the way, the circle is this blue curve that I've drawn. The circle is not the disk. See, the circle together with the inside is called a circular disk, okay? But the circle itself is just the curve. And the perimeter, meaning the length of that circle, is called its circumference. In other words, basically, if you have a circular region, the circumference is the distance around. And the special vocabulary that we use is, if you draw a line from one point on the circle to another point on the circle, from one point to any other point, that line is called a chord. But if it happens that that line goes through the center of the circle, that special chord is given the name diameter. See, di is 2, and meter measures. See, the diameter cuts the circle into 2 equal parts. By the way, somebody says, how do you know that one's the diameter? Why isn't this one the diameter? Well, what's nice about a circle is that no matter what direction you look at it in, it's all the same shape. In other words, imagine this to be a wheel. As the wheel rolls, notice that the diameter will take on a different direction. See, no matter how a wheel turns, whenever it stops turning, it still looks like the same wheel. And half of the diameter, that means any distance that goes from the center of the circle see the center, to the circle itself is called a radius. So in other words, this is a radius, this is also a radius, this is a radius, and from this you can see that two radiuses, which are called, two radiuses are called radii. See, two radii, that's a Latin word, makes up the diameter. Okay, that's just the basic vocabulary. How are you going to learn it? You memorize it, the same as any other vocabulary. A few words to learn now, right? Circumference, diameter, radius, and if you feel like it, memorize what a chord is. Now what I wanted to point out is that all circles have the same shape. See, look at this circle here. Look at this circle I've drawn down here. They do not look alike in the sense that they have different sizes. But if I didn't tell you, you would not know whether this circle here was a shrunken version of this one or whether this one was an enlargement of this one. In other words, if I were to take this circle here and blow it up to a certain size, when it eventually had the same radius as this circle up here, the two circles would look alike. See, those are called similar. When two figures have the same shape but different sizes, they're called similar. And why is similar so important in our course? Notice that in our course we've been stressing ratios. And when two figures are similar, they always keep the same ratio. And let me show you what I mean by that. Let's suppose this is a photograph, and in this photograph, the blue object and the purple object that are here, and they're separated by a certain distance, have a certain relationship to one another. The purple, I've drawn the purple line to be twice the height of the blue line, okay? Now somebody says, I want you to double the size of the picture. I want you to give me a true enlargement that doubles the size. So I draw this to double the size. What's going to happen? This length here becomes twice its length. In other words, there's no danger of confusing the red length with the blue length. They're quite different. The purple length also doubles in length. It becomes the length indicated by the green length, okay? The distance between these two lines will also have been doubled. But the part that stays the same is if I take the green length and divide it by the red length, I will get the same quotient as if I took the purple length and divided it by the blue length. See, the beauty about similar figures is that even though they have different sizes, their shapes are in the same proportion. And you might be interested in knowing that even before the birth of Jesus, back in ancient Greece and ancient Egypt, people were computing heights of tall buildings and trees and how far across a river was just by using what we call similar figures. Let me give you an idea. Suppose this was a big, steep hill or a building that people couldn't climb, and they wanted to find out what the height of this building was. What they would do is they would take a stick and put it in the ground, a stick that was short enough so that they could measure its height. Then what they would do is they'd wait for a sunny day. You need the sun for this trick, okay? And what you would do is they couldn't climb the building, but they could measure what the length of the shadow was. And they could also measure what the length of this shadow was. But they could also measure the size of the stick. That was the one they put up. And so what they simply said is the ratio of this black line to its shadow must be the same as the ratio between this black line and its shadow. In other words, this divided by this must be the same as this divided by this. For example, I'll just make up some numbers here. If this shadow was, say, 2 feet long, and this shadow here was 20 feet long, and this stick was 6 feet tall. See, what they would say is that 2 goes into 20 10 times. There's our common fraction problem again. Since this shadow is 10 times as long as this shadow, the height of this building must be 10 times the height of this stick. Therefore, since the stick was 6 feet high, the building must have been 60 feet. A pretty powerful device. And by the way, I'd like to pause here for just a second to let you in on something. You know, we talk about high tech, we talk about calculus, we talk about all these advanced subjects. You know, the material that we're talking about now, and I address this primarily or especially to people who haven't been intimidated by the material yet. You are on the frontiers of higher mathematics here. Some of these concepts, which seem so simple, are really the foundations of some very advanced mathematics. And by the time today's discussion is over, I hope to show you some things in terms of something called integral calculus, in terms of technology, in terms of all kinds of things that come up that show you that we're only a small step away from doing some very complicated things. In fact, the steps are not really that great. It's sort of like saying that French 2 is more difficult than French 1. But it's easier to go from French 1 to French 2 than from knowing no French at all to French 1. In a certain sense, advanced mathematics is more difficult than arithmetic. But it's actually a simpler step to go from mastery of arithmetic to mastery of other topics than it is to go from no feeling of arithmetic into the mastery of arithmetic. Remember, don't confuse the person who knows how to manipulate numbers with the person who knows arithmetic. Arithmetic is not just a skill, it's a philosophy. And this is the theme that I hope has emerged through this course, and I've taken the opportunity to pontificate here a little bit because we're coming down. After today, we have what? One module left. So whatever I don't say in the next few lectures goes unsaid, and that would be a tragedy, wouldn't it? Anyway, let's go back on with this. You see, the thing I'm driving at is that in the same way that you can use ratios over here, you also use ratios with circles. You see, since all circles have the same shape, remember I showed you a big circle and a small circle? Let's C with a 1 under it, we'll call that C sub 1, stand for the circumference of the first circle. And let D sub 1 stand for the diameter of the first circle. And let C sub 2 stand for the circumference of the second circle, and D sub 2 stand for the diameter of the second circle. See, the big circle has, of course, a bigger circumference than the small circle. The big circle has a bigger diameter than the small circle. But since the two circles have the same shape, they are proportional. In other words, if I take the first circumference and divide it by the first diameter, I will get exactly the same answer as I would if I took the second circumference and divided it by the second diameter. In other words, in any circle, if you take the circumference of that circle and divide by the diameter, no matter what circle it is, the result will always be the same number. And by the way, it's a pure number, because if the circumference was measured in feet and the diameter is measured in feet, feet divided by feet cancel and you get a pure number. If the circumference is in meters and the diameter is in meters, meters divided by meters cancel. See, that constant is a pure number. The ancient Greeks gave that constant a name, and they picked the Greek letter pi. See, people wonder why we use Greek letters. That was the only alphabet the Greeks knew. They're the ones who started all this stuff. In fact, when you say to a person, can you do geometry, and they say it's all Greek to me, that means they already know more than they thought they did, because it was a Greek contribution. But basically, what they found was, and I will indicate later how this was done, what they found is that this constant was a number that was, well, it's not a simple number. In other words, the ratio between the circumference and diameter has to be something. They measured the thing out, and I'll show you later how they measured it, but what they found was that to 5 decimal place accuracy, that constant was 3.14159. In fact, you might be impressed to know that even though Archimedes lived in an era in which there was little technology, there were no automobiles, there were no televisions, there were no electronics, Archimedes, with his knowledge of mathematics, was able to show, and look at how refined this is, that the number pi was more than 3 and 1071st, but less than 3 and 1/7. That was how closely he measured it. By the way, in many grade school books, they give pi as 3 and 1/7. If you write 3 and 1/7 as a mixed number, you get 22/7. 22/7 is a improper fraction, so writing it as a decimal, you get 3.142 something, which, by the way, is not 3.14159 something. See, when they notice again, estimating and rounding off. If you're going to say that pi is 22/7, notice that that only agrees with the established value of pi up to 2 decimal place accuracy. In other words, if you want more than 2 decimal place accuracy, you can keep writing this decimal out to as many places as you want, but the approximation won't get any better because the approximation is already wrong over here. In other words, when you use 22/7 for pi, 3 and a 7th, you're assuming that you're only measuring accuracy to the nearest hundredth. Some calculators actually have a pi key on them. In other words, it's a key with the letter pi in there. And basically, all you have to do to multiply by pi on that kind of a calculator is you enter the number that you want multiplied by pi, press the pi key, and that will multiply by pi for you. See, if you want to add pi, you hit the plus sign, then press the pi button. If you want to divide by pi, you press the divide button, and then you press the pi key. And that avoids you having to remember all the decimal places in pi. In our course, unless otherwise specified, we will let pi be 3.1416. We'll round it off that way. And by the way, here's an interesting psychological thing. When I was taught circles, people never taught me that all circles had the same shape. All they told me was that to find the circumference of the circle, you take its diameter and multiply it by this magic number called pi. I thought what you might like to see is where that comes from. You see, basically, if the circumference divided by the diameter is pi, isn't that the same as saying the circumference is pi times the diameter? In other words, if I say that 6 divided by 2 is 3, isn't that the same as saying 6 equals 2 times 3? See, basically, these two things say the same thing, but psychologically, I find it easier to remember it this way, because what this tells me is what? All circles have the same shape. The circumference divided by the diameter is always the same number, and we call that number pi. See, calling it pi was one thing. Determining that pi was 3.14159, etc., that was something else. But it had to be something. It just turned out to be that. See, but when you write it in this form, that tells you a simple way to convert the diameter into the circumference. By the way, sometimes people prefer to work with the radius of the circle rather than with the diameter. Remember that the diameter is just twice the radius, so whenever you want to, you can replace the diameter by twice the radius. So you can say that the circumference is what? It's pi times 2 times the radius. As we'll talk about in our next lecture, whenever you're using letters of the alphabet, it's difficult to use the time sign because the time sign looks too much like the letter X, and that could cause confusion. So in many math books, whenever there are letters being used to denote numbers, when you want to multiply, you just put the numbers next to each other, or the letters next to each other. So in many math books, instead of seeing that the circumference is pi times the diameter, they'll write it as C equals pi d, and put the pi and the d right next to each other. And if they're using the radius, they'll say 2 pi r. And how do you read that? You start with 2, multiply by pi, then multiply that by r. And rather than ramble on this way, let's just actually do a few problems. Problem number 1 says, find the circumference of a circle if its diameter is 5 feet. You see, we're going to lecture on this also as our last enrichment lecture, a couple of lectures down the road. I try to explain to you where this formula comes from. But if you don't know where this formula comes from, but you're willing to accept it, you're in good you're fine. You're fine. In other words, the only difference between understanding this and accepting it is that when you understand it, you have the additional confidence of knowing that the result is valid. When you don't understand it, you're taking somebody's word for it. So suppose I hadn't explained to you how this relationship comes about. I could say to you, given the formula that C equals pi times d, where pi is 3.1416, find the value of C when d is 5. See, all this formula says is what? Starting with the diameter, multiply it by pi, and the answer will be the circumference. So pi is given to be 3.1416. Remember, we said that's what we're going to use here. The diameter is given to be 5. And by the way, answers are supposed to have labels, so I put feet in parentheses to remind me that the diameter is modifying, that the 5 is modifying feet. There's no label after the 3.1416 because that's a pure number. And now what do I do to get the answer? I just multiply 3.1416 by 5, which I can do longhand or by a calculator, and put the answer in feet, and the answer is 15.708 feet. But usually when we measure feet, the fractional part is in inches, so what we have is what? 15 feet plus what? 0.708 of 12 inches, and that's roughly another 8 inches. So if you're going to write this in to the nearest inch, the answer would be what? 15 feet, 8 inches, okay? Now you still have to read the problem carefully. You have to make sure, see, remember in this formula, you multiply by pi to get the circumference only if you start with diameter, okay? Secondly, what the label is going to be depends on what the label of diameter is. For example, the next problem says, find the circumference of a circle if its radius is 5.2 meters. This does three things for me. First of all, notice the word radius got in here instead of diameter. Secondly, notice that instead of a whole number, I'm dealing with a fractional part. And thirdly, notice that I've brought in the metric system. So what? The circumference is still pi times the diameter. However, the 5.2 isn't the diameter, that's just the radius. The diameter is twice the radius, so if the radius is 5.2 meters, the diameter is going to be twice that, which is 10.4 meters. So what do I do now? To find the circumference, pi gets replaced by 3.1416. The diameter gets replaced by what? 10.4 meters. See, remember the answer is in meters now. I now multiply 3.1416 by 10.4, okay? And the answer comes out to be, and I write approximately because this isn't exactly pi, it's 32.67264 meters. Here's the nice thing about the metric system. Suppose I want the answer to the nearest millimeter. Just for the sake of argument, I want the answer to the nearest millimeter. Remember, if these are meters, see, what's a millimeter? It's a thousandth of a meter. Tenths, hundredths, thousandths. All I have to do to round this thing off to the nearest millimeter is I write down the 32 meters, then the millimeters column is over here. The digit to the right is more than 5, so how would I read this? 32 meters, 673 millimeters. And by the way, I'm not suggesting that you have to do this, but I think it might be fun, just for you to get a feeling for this, is to take a circle, in other words, pick your own radius, take a circle, draw it, then take a piece of string and wrap the string around the circle so that you can actually measure the circumference, like a tape measure. And actually see that if you were to take the diameter and multiply that by 3.1416, you would get that circumference. Do you see the idea here? I would like you to practice on things like that. And by the way, I also want you to learn to understand that no matter how advanced we get, certain problems still remain the same. There are going to be many problems that look like multiplication problems, but they're division problems. How many times in this course, and this is a rhetorical question, don't all answer at once, but how many times in this course have we played around with things like 2 times blank equals 15, which looks like a multiplication problem, but it's really a division problem? See what happens over here? Next problem says the circumference of a circle is 20 feet. To the nearest inch, what is the radius of the circle? See, what happened in the previous problem? In the previous problem, we started with the radius and found from that the circumference. Now we're starting with the circumference and we have to find the radius. You see, the formula doesn't change. In fact, let me give you a quick introduction into Module 12 as to what the difference between arithmetic and algebra is. C equals pi times d is neither arithmetic nor algebra. It's a formula. And by the way, this particular formula is used in high tech over and over again. I mean, we're working with serious stuff here. But the point is this. If I'm given D and want to find the value of C, that's arithmetic because all I have to do is multiply D by pi. If, on the other hand, I'm given C and I want to find D, you see, isn't that what's happening in this problem? See, the 20 feet is what C is, not what the diameter is. See, this is the 20 feet. To find the diameter, it looks like a multiplication problem, but I'm going to have to divide. So because I'm given the answer and want to find out what one of the factors is, now it's called algebra. You see, the formula by itself is neither arithmetic nor algebra. But if I'm given D and want to find C, that will be arithmetic. If I'm given C and I want to find D, that will be algebra. And why is that algebra? Because even with the calculator, I have to think before I can put the answer down. You see, when I see the problem like this, the calculator can't solve the problem in this form for me. I have to make the judgment that this says what? The diameter is 20 feet divided by 3.1416. See, that's where the algebra comes in, and I will teach you more about that in the next module. Here's where the calculator comes in very handy. That's why they call it a hand calculator, because it's very handy. You see, you could divide this out longhand, but it's a real mess. On the calculator, you divide this by this, and instantly this appears. By the way, be very, very careful. Remember, pi is 3.14159. This is already rounded off. This may look like a tremendous number of digits, but remember, the answer can't be more accurate than the least number of significant digits that you had to start the problem with. This is mathematics' answer to a chain is no stronger than its weakest link. This may look impressive, but anything after the 4th decimal place is in doubt. But we won't worry about that. As long as the calculator gives us that, we'll leave it on the calculator. That's what's nice about the calculator. Now, what's wrong with the answer so far? What's wrong is that we weren't asked to find the diameter, we were asked to find the radius. How is the radius related to the diameter? Well, since the diameter is twice the radius is half the diameter. The radius is the diameter divided by 2. Here's the nice thing about the calculator. This number is already on there. Leave it there. Now press the division button, hit the 2, hit the equal sign, and now this comes up right away. You don't even have to copy this over, you see. You can leave all the calculations in the calculator. And if you have one that prints on paper, that's even nicer because you can keep a permanent record of what your computations were, and it makes it easier to check. See, the problem with a regular calculator is if you want to check the thing over, you have no record of what you've done. You probably just have to repeat the problem. So the radius is 3.183091419 feet, but the problem says what? Find the radius to the nearest inch. So I have to I know it's 3 feet, but how many inches? And it's not 18 inches, and it's not 1.8 inch. What you have to remember is that this stands for 3 feet plus this fractional part of a foot. A foot is 12 inches, so it's this fractional part of 12, which comes out to be 2.197. So to the nearest inch, this is 3 feet, 2 inches. Well, time is running on. So much for perimeter, which plays the role of circumference. How about area? And what I'm going to show you next is exactly how the subject called integral calculus began in Greece in roughly the 6th century BC. I would like to find the area of this circle. And the area is the amount of space contained inside the circle. The one thing I know how to find the area of is a square. So one of the devices that the ancient Greeks used was they said, okay, let's draw a square around the circle. Since the circle is inside the square, its area must be smaller than the area of the square. Well, let's take a look over here. From here to here is the radius. From here to here is the radius. So from here to here is also the radius. Notice that the length of the line from here to here is the radius. The length of the line from here to here is the radius. So what's the area of this square over here? The area of this square is r times r, right? It's r squared. How many of these are there in the big square? There's 1, 2, 3, 4. So if I took the radius and squared it and multiplied that by 4, that would give me this whole area over here. What's the area of the circle? Less than 4r squared or more than 4r squared? It's less than 4r squared. Therefore, it must be pi r squared, right? No. That's what my son would say. But basically, there are lots of numbers that are less than 4. See, what I know for sure is that if I want to find the area of a circle, if I take the radius and multiply it by itself, and isn't that vaguely reminiscent of how you find the area of a square? You multiply the length by itself? Well, it should be, because that's what we just did. We found the area of the square. And so what I'm saying is, if I take the radius of the circle, multiply it by itself, then multiply that by 4, what am I sure of? I'm sure that whatever that answer is, that's too big to be the amount of space inside the circle. What the ancient Greeks, Archimedes in particular, and a fellow named Aristosthenes, you like that? Aristosthenes, okay? This was called the method of exhaustion, not because it physically exhausted you, even though it did, but it exhausted the space. See, what they did was they first drew the big square. That gave them an answer that was too big. Then they took these 4 points over here and joined them. That's that black figure in here. What did that give me? That gave me a square that's inside the circle. So if I can find the area of this square, that will be too small. You see the upper and lower bound again? I can find one area that's too big, one area that's too small. Now, can't I inscribe more and more straight line segments around here? In other words, I can squeeze in one region that's too small, another region that's too big. And I put the squeeze on this region, and to make a long story short, even though we'll do a little bit more of this later, to make a long story short, what the ancient Greeks were able to determine was that pi was the correction factor to convert the r squared into the area of a circle. In other words, if you want to find the area of a circle, you start with the radius and square it, the same way as you'd find the area of a square. But then you multiply that by pi, and that will be the area of the circle. For example, to the nearest square inch, what is the area of a circle if its diameter is 20 inches? Well, what's the formula going to be? The formula is you start with the radius, you square it, you multiply by 3.1416. And by the way, that's another thing we're going to be doing in the next module. Somehow, when you look at A equals pi times r squared, can you see a number anxiety, a formula anxiety starting that way? You say, oh my God, a formula, I can't handle it. All this formula does is that it's a second language, a precise scientific language for saying start with r, square it, multiply by 3.1416. You see, if this doesn't scare you, I was going to say square you. If this doesn't scare you, but this does, it's a language problem, not a math problem. If both of these scare you, I've been a failure, okay? Which I may be anyway, but don't worry about that. So we're starting with a diameter of 20 inches. What's the thing I'm supposed to square? The radius. Well, if the diameter is 20 inches, the radius is half of that, which is 10 inches. If I square 10 inches, and be careful here, 10 inches times 10 inches is not 100 inches, it's 100 square inches. And what do I do next? I multiply that by pi, that's 314.16 square inches, which rounded off to the nearest square inch is 314 square inches. And notice how I write this, with that little 2 up here, to remind you that you've multiplied inches by inches, and that's supposed to remind you that you're finding the length you're finding the space inside the circle, not the circumference. And see, don't confuse this problem with the problem of where you took the diameter, which was 20 inches, and multiplied that by 3.1416. 20 inches. See, if you do that, the answer comes out to be not square inches, but inches. You get 62.832 inches. And that's the same as 63 inches. There's no square there. That means you're finding the distance around. And again, even if this sounds boring, take a piece of graph paper where the things are marked off into small squares. Draw a circle whose diameter is 20 inches. Draw that circle. Measure the distance around. See if it doesn't come out on your scale to be around 63 inches. Measure the amount of space inside. See if it doesn't come out to be about 314 square inches. And what that means is, if you took 314 one-inch squares and rearranged them and sliced them up properly, they would fit snugly inside the circle, okay? Now, let me show you another definition of a circle that's kind of interesting. In problem number 3, we saw that if the circumference of the circle was 20 feet, the radius was 3.183091419 feet, whatever that came out to be. Okay, that's a given. I could have asked you to go back and look at that, but rather than have you get a headache flashing back over what's been done before, I just reproduced problem number 3 over here. Now, once I know this, can I find the area of the circle itself? See, how do you find the area of the circle? You take the radius, and by the way, this is great in the calculator. If this is already in here, some calculators already have a special key that looks like this. It's the opposite of the square root key. It's called the squaring key. And what we do is, when this number is in here, if you just press this key, you get to square that number right away. But basically the idea is this. Start with this number, you square it, then multiply by pi, and that will give you the area. In other words, what is the area of this circle to the nearest square foot? You start with the 3.18309, you square it, you multiply that result by 3.1416. That comes out on my calculator to be 31.8309 something or other square feet. Since I'm only interested to the nearest square foot, the fact that this is an 8 over here allows me to round this off to 32. But if I wanted a more precise answer, I could say that the area was more than 31 square feet and less than 32 square feet, okay? Now, the reason I'm bringing this up is you may recall that in our previous lecture, we were talking about the fact that if you had 20 feet of material, you had 20 feet of wiring, and you wanted to enclose a rectangular plot, that if you formed a square, that would enclose the largest area, okay? Remember that? Of all the given rectangles that can be formed with a given perimeter, the square encloses the greatest area. But that was under the constraint. That was under the constraint that you form a rectangle. Could you visualize that if you had to take a piece of string, tie the ends together, and somebody says to you, spread out the string so it encloses the largest amount of space? Can you visualize forming a circle that way? You don't have to, but can you see that would happen? In other words, as you try to stretch this thing out to enclose as much space as possible, you get a circle. Let me show you how this works in terms of a problem. I say to you, what is the area of a square whose perimeter is 20 inches? Okay? 20 inches. I used feet before. I just inadvertently switched to inches here. If this bothers you to make it more exact, we could call it feet. You don't have to. Let's just call it 20 inches. Okay. Well, I formed this into a square. If the whole perimeter is 20 inches, 1/4 of the perimeter would be the length of the side of the square. You see, if I add up all these 4 equal sides, that has to come out to be 20 inches. So each side must be 5 inches. And if I have 5 inches by 5 inches, that's going to be what? 25 square inches inside here. See, 5 inches times 5 inches. 5 times 5 is 25. Inches times inches is square inches. Now let's form another rectangle whose perimeter would be 20 inches. If the perimeter is going to be 20 inches, half the perimeter, which is the length plus the width, has to be 10 inches. So for example, suppose now the length is 7 inches and the width is 3 inches. See, the perimeter will still be 20 inches. 7 inches times 3 inches gives me 21 square inches, and that shows me that the square whose perimeter is 20 inches has a bigger area than the rectangle, which is 7 inches by 3 inches, even though the rectangle has the same perimeter as the square. But the part that was interesting is I work with feet. Can we just come? No, we don't even have to come back to this. I was going to come back to it, but I don't even think you have to see it. What I had done was that I'd worked with 20 feet over here, and what we showed was what? What we showed was that if the area of the circle, if the perimeter, the circumference of the circle was 20 feet, the area would be between 31 square feet and 32 square feet. Is it clear that if I just change the label from feet to inches, the arithmetic would stay the same, but only the label would change? In other words, if I say that the area, or if I say that the circumference is pi times d, whether I use 2 feet, 2 inches, 2 centimeters, 2 miles, pi times d will be 2 pi, only the label is going to change. So all I'm saying is that if we had been working with inches over here, the area of the circle whose perimeter is 20 inches would have been between 31 square inches and 32 square inches, which is more than the 25 square inches over here. Now the problem that really becomes interesting is I have shown you the circle because in real life most rates are non-constant. And that means if you were to graph them, they don't graph as straight lines. And it turns out that the circle is almost an adopted member of the straight line family. Even though it's not a straight line, it has such a symmetry to it that it almost behaves like a straight line. It's as easy to draw as a straight line just about. It's as easy to measure, all these different things. But the question that comes up is, what do you do if the situation is such that you have a non-straight line boundary and you want to measure the amount of space inside when the region isn't a circle? And I thought I would like to show you another brilliant example of what the ancient Greeks were able to do with their logical minds. You know, the Greeks are said to have been the founders of geometry, yet the pyramids were built thousands and thousands of years before the Greeks developed geometry. You see, the Egyptians knew how to use geometry. The greatness of the ancient Greeks wasn't that they did geometry, it was they started with 10 assumptions, 5 of which were called axioms, 5 of which were called postulates, and based on those 10 assumptions, they derived 14 complete books of inescapable conclusions, portions of 5 of which make up the traditional high school geometry course today. That's how powerful the Greek logic was. It wasn't that they showed what was true geometrically, they showed why it had to be true. And I thought that at a level that we could comprehend, I would like to show you how the ancient Greeks, once they knew that the area of a rectangle was the length times the width, were able to parlay that into finding the area of any region, no matter how complicated it looked. And we'll begin with a very neat device that surveyors still use today. It's called the method of triangulation. And it's called a strategy for finding area. A rectilinear region simply means a region all of whose boundaries are straight lines. Like, look at what I've drawn in red over here. It's certainly not a rectangle, but are all the boundaries straight line figures? Straight lines. Yes. So this would be called a rectilinear figure. Basically, whenever you have a rectilinear figure, take any two consecutive sides. See, consecutive sides means that they meet at a particular point. See, look at this line and this line. Join their endpoints. Now look at this line and this line. Join their endpoints. Then, for example, look at this line and this line. Join their endpoints. And to make a long story short, do you see that this construction allows me to break this region down into a bunch of rectangles? Triangles. Okay? Triangles. Suppose, for the sake of argument, I knew how to find the area of a triangle, how much space there was in a triangle. Do you see that since I now have broken this down into 4 triangles, I can find the area of each triangle, add those up, and won't that give me the area of the whole region? So what the ancient Greeks said was, look, we can find the area of any rectilinear figure just by knowing how to find the area of a triangle. But how do we find the area of a triangle when all we know how to do is to find the area of a rectangle? So the first thing they did was they went from the well-known to the slightly less well-known. Rather than a rectangle, they took something that was called a parallelogram, of which a rectangle is a special case. You see, a parallelogram is a 4-sided figure in which the opposite sides have the same direction, but the corners aren't necessarily square. See, if the corners are square, it's called a rectangle. A rectangle has a base and it has a height. Now, the question that the ancient Greeks were confronted with is, knowing how to find the area of a rectangle, how do you find the area of a parallelogram? And they did something real cute. What they noticed was, if they took this little piece over here and chopped it off, it fit very snugly over here. But now if you look at this figure, that's what? It's a parallelogram. The parallelogram has now become a rectangle. The area of a rectangle is the base times the height. But since we got the rectangle by taking a piece of the parallelogram and just putting it here, if I now take that piece and put it back over here, I haven't changed the area at all. I've just realigned it. So the area of a parallelogram, believe it or not, is also the base times the height. Not the length times the width, the base times the height. Now came the problem of how do you find the area of a triangle. And what they said was, look, here's this triangle. That's in purple over here. What they said was, through this point, let's draw a line that has the same direction as what I call the base of the triangle. So they did that. Then they said, through this point, draw a line that's parallel to this side. Do you follow what I've done over here? What's this done? These two sides are parallel. These two sides are parallel. Therefore, this whole region must be a parallelogram. And the area of a parallelogram, we just saw, was the base times the height. But we don't want the whole parallelogram. All we want is this little purple triangle. Do you notice that this triangle and this triangle that make up the parallelogram have the same shape? In fact, they even have the same size. Therefore, if this triangle is half of the parallelogram, if the area of the parallelogram is the base times the height, the area of the triangle must be 1/2 of the base times the height, and that becomes the formula for the area of a triangle. You take the base of the triangle, multiply it by the height. Which side is the base? Whichever one you stand it on. That's a very amazing result. This is amazing. Whichever side you take, multiply that by the corresponding height, and the answer will come out the same no matter which of the 3 sides you started with. And the important point is what? To find the area of a triangle, you multiply the base times the height, and then take half of that. It's called 1/2 BH. And once you know the area of a triangle, you can find the area of any rectilinear figure. And what the ancient Greeks did was they learned to build by rectangles. Back in 600 BC, if you had said to Archimedes, find the area of this region. See the region over here? It's this line, this line, this line, and then this curved portion over here. See, what Archimedes would do is he would divide this region into 4 equal parts. Then what he would do is he would draw these lines in. Then he would take the lowest point in each part, and he would draw a line like this. You follow what I'm doing here? And he would form these rectangles. Could he find the area of each of these rectangles? See what I'm saying over here? This is a rectangle, this is a rectangle. He's divided this up into rectangles. He can find the area of each rectangle, it's the base times the height. He adds these up. That gives him the area of this region over here. It's the one that goes like this. I can't draw it that well. But that's inside the region he's looking for, so whatever the area is, it's less than this amount over here. Then what he does is he looks for the highest point in each region. See, now he draws this rectangle. See, he draws this one. Then he draws this one. Then he draws this one. Then he draws this one. Now you see, he can find the area of each of these 4 big rectangles. But since the 4 big rectangles enclose the purple region, that area must be too big. So now what he's done is, he says, I don't know what the area is, but it's less than this number, but bigger than this number. And then what he could do is what? Make more and more subdivisions here, and so the underestimates would get bigger and bigger, the overestimates would get smaller and smaller, and he would then squeeze the true area between these 2 bounds and eventually squeeze out the exact answer. And if that seems difficult, it really isn't difficult, it's complicated. And that complication is precisely what numerical integral calculus is all about. That basically integral calculus says, how do you find the area of a region if its boundary isn't made up of straight lines? So you see, integral calculus is an outgrowth of elementary geometry. And differential calculus says, how do you find the rate of change when it's not constant? So in that sense, differential calculus is an outgrowth of rates of change. And I thought that I would conclude today's lecture with getting back to a metric thing, trying to show you in terms of areas, roughly speaking, why a hectare is roughly 2.5 acres. And I just wanted you to see that in terms of areas. See, use the fact that 100 meters is about 1/16 of a mile to show that a hectare is approximately 2.5 acres. And remember what? An acre is 1/640th of a mile. In other words, it takes 640 acres to make a mile. A hectare is a square, each of whose sides is 100 meters. So 1 hectare is 10,000 square meters. And now I wanted to show you in terms of areas how easy it is to figure out what an acre is compared to a hectare. You see, let's start with a square mile. A square mile means 1 mile times 1 mile. If 100 meters is 1/16 of a mile, 1,600 meters is a mile. So we'll call that approximately a true statement. So a square mile is 1 mile by 1 mile. It's also 1,600 meters by 1,600 meters. An acre is 1/640th of a square mile. So that means if you take a square mile and divide that by 640, that will tell you what an acre is. But a square mile is 1,600 meters by 1,600 meters. So I divide that by 640. I could do that on a calculator, but I don't want you to become too calculator dependent. I would like you to notice, for example, that 640 breaks down very easily into 8 times 80. Then you could say 8 goes into 1,600 200 times, okay? 80 goes into 1,600 20 times. 200 times 20 is 4,000. So an acre is approximately 4,000 square meters. And once you know that, it's just a matter of going back to Module 3 and counting by multiples of acres and square meters. See, if 1 acre is 4,000 square meters, 2 acres is 8,000 square meters, 3 acres is 12,000 square meters. See, I'm counting by 1s here and by 4,000s here. And we said what? A hectare is 10,000 square meters. So by constant rates, since 10 is halfway between 8 and 12, you see the number of acres will be halfway between 2 and 3. That's 2.5 acres. Or another way of saying it is, if 1 acre is 4,000 square meters, to find out how many acres there are in 10,000 square meters, you just divide 10,000 square meters by 4,000 square meters. And look at how much of this is the same stuff we've done before, you see. We cancel here, we cancel here, here, here. This becomes 10/4. We reduce that to 5/2. That's the same as 2.5. And that checks very nicely with the fact that the exact amount is what? 2.471 acres in a hectare. And what I've tried to do here is several things. There are a lot of things I've tried to do, but the most important thing I'm trying to show you is that if you have mastered the concepts that came up in the first few modules, if you're willing to allow your mind to expand your horizons and not to be frightened, that what we do in advanced mathematics is just many, many separate small steps of elementary mathematics. And we're heading now for the wrap-up of this course because the final 2 enrichment lectures will be on arithmetic as the gateway to algebra. What I intend to show you is that algebra is nothing more than a new and not too difficult way of looking at arithmetic. I always like to end one course by giving the prelude to the next. And I always like to start a course by showing how it feeds off the end of the previous course. We'll get to that all in due time. But until that time, the usual motto, study hard, have fun, stay young.